Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu, and in this video, we finally walk into the chapter 6. We're going to talk about energies in this chapter. So first, let's start with the interconversion of energies. So first, let's talk about interconversion of energies. What is exactly the energy? You may have heard about the word energy before, and yes, you can understand basically the same energy as used here. In the scientific word, though, we need to have a unit for energy, and that's in the joule, and spelled as J in the SI unit. Also, the energy has many other units, saying calorie in cal, British thermal unit, BTI, and the conversion between these different units are listed here. 1 cal equals to 4.184 joule, 1 BTU equals to 1055 joule. So you probably heard about these calories before. The energy are everywhere. You know, it's in the moving parts, it's in the food, it's in the fuels, and it's everywhere. Okay. However, if we put energy into different categories, there are only two big types of energy. One is called potential energy, and the other is kinetic energy. Kinetic energy means the energy involving a moving part. Okay, something is moved, something moves. While the potential energy is, the other whatever energy that is not kinetic energy, that does not move. So let's just talk about a few examples. We can have fossil energy. We use that to burn and give us heat, right? We cook. And also we have wind energy, uses turbines that can move. So this wind energy is actually a kinetic energy. Then we can have electricity and electrical energy, where you use all the electricities in the light bulbs in your house. Also nuclear energy, and also mechanical energy, such as the fast moving boat. The mechanical energy is also a part of the kinetic energy. Okay, and we have these so many forms of energy. These energies can convert between each other. We call that interconversion of energies. And it's also called energy transfer. There are two forms of energy transfer. So there are two forms of type of energy, and also there are two forms of energy transfer. One is through heat. Okay, we can use a Q to representing the heat. Is a thermal energy. Okay, so heat means the difference in temperature between the system and the surroundings. Okay, a system is an object or material or a group of objects that you defined as, as a group together. The surrounding is whatever else of the objects you defined. So the other types for energy to transfer is through work, or we can use W to representing the work. The work means an object is moved by a force. We're going to give you detailed examples on how the heat and work happens during the energy transfer. So for a system can be a boat, can be a person, can be a sample, can be anything, okay, or sample with the container. So for a system, like whatever you define it, the whole system, the change of the energy equals to the final state of energy minus the initial state of energy. That equals to Q plus W, okay, equals to the heat and the work. The delta, Greek letter delta, means the change. So delta E means the total change in the system's internal energy. Okay. As you can see, Q and W, both heat and work, refers to a change of status. So if you just given the object at a certain temperature, you cannot say it has heat. It only has a change of temperature, then you can see there is a heat transferred. The same thing as work. If you just see a static object there is no work done. It has to move for a certain distance, then you can see the work is done. Okay, And here, when we talk about energy, change of energy equals to work plus heat. The definition of positive and negative of Q and W are new. It's not the numeric value you had before. So in this system, the positive value of Q means the absorbed heat. The negative value of Q means the released heat. Well, for the W, the work, if the work is done onto the system, then it's positive. If the work is done by the system to the environment, then it's by. Okay, and then it's negative. So you need to be careful about this definition of Q and W. Let's take a look at a few examples. First, energy transferred as a heat. Now we have a beaker with some water. Initially, the water is very hot. Okay, so the system we can define as a beaker and water together. Okay, it was hot. After a while, it cools down to room temperature, right? So the final state is room temperature beaker and water. So if you compare the initial and final, there is a temperature difference. The temperature of the system, the water and beaker, dropped. So because of the dropping temperature, we can say the heat is released to the surroundings. So itself, the temperature dropped. And we say the Q is less than 0. In another case, we have ice water still in the beaker. We define the ice, water, and beaker as a whole system. Initially, the temperature is low because we have ice. And after let it sit in the room temperature for a while, the temperature increased, the ice melt, right? So finally, we have a whole system including beaker and water, or the melted ice, to have an increased temperature. Because that temperature increases of the system, we can say the heat is absorbed from the surroundings to the system, and the Q is larger than 0. Okay, let's take a look at the work. Now, it's a device made by a system, and on top of this system, there is a trapped volume of gas. Okay, so initially we have the acid reacting with zinc in this devices. So we are producing some gas from this chemical reaction. Initially, the gas produced is small because the chemical reaction probably just started. It hasn't produced much yet. So you can see the plug is in the relatively small, like lower position, a smaller position. However, after the reaction is done, completely done, in this case, we define the volume above the liquid acid, the liquid phase of the acid, including the liquid, including the zinc as a system. Okay, after the reaction is done, zinc, it becomes the zinc ions that's still in the solution, so they're still within our system. We don't, the system is still valid. So after the reaction is done, there is a lot of hydrogen produced. The hydrogen gas will push this plug to further away, right? For this system, the plug is not the part of the system and is pushed further away. So in other words, we can see the volume, gas volume, or the total volume of the system expanded. The volume increases. We say the work is done by the system to the surroundings. It pushed this plug away, right? So we say the work, the value of W, the work, is negative, smaller than 0. In another case, we have, the final status before. We have a system with liquid with some gas. We have a plug, right? So, and we define the gas volume plus the liquid as a system. If we manually push the plug to the left, so the volume of the gas decreases. In this way, the surrounding does work to the system, right? So the work is positive. When you meet in questions and it asks you whether the work is positive or negative, I highly suggest you to refer to the volume. Okay, so in the second case, the volume decreases. You can see the volume decreases as we push the plug from right to left. The volume decreases, the work is done by the surrounding to the system. The work value is larger than 0. Okay, so to a brief summary, how to define whether the work or heat is positive or negative refers to the temperature and the volume of the system. Okay, if the temperature increases, the system absorbs heat from surroundings, the Q is plus. If the volume expands, the system does work to the surroundings, the work is negative. All right, let's take a look at a question about energy conversion problem. A sample of liquid absorbs 13.5 kilojoules of heat and does 1.8 kilojoules of work when it evaporizes. Calculate the change of energy in the unit of joule. Okay, so this is a direct application of the equation delta E equals to Q plus W, right? So first we need to define the value of Q and W. So for Q, it says it absorbs energy, right? Absorbs energy, the Q is positive. So Q equals to 30.5 kilojoules. Since the final answer needs a unit in joule, we can convert the kilojoules to joule. Okay. Then let's take a look at the W. The liquid evaporizes. So it's turning from liquid to gas. Then imagine the same mass of liquid turning to the same mass of gas. The volume will expand, right? So it evaporizes, the volume expands. The system does work to surroundings, so the work is negative, right? Plug in the numbers, the work W equals to negative 1.8 kilojoules. Convert that to joule, it's negative 1,800 joules. So then you can calculate the delta E, the change of energy. Delta E equals to Q plus W, just plug in the numbers, 13500 plus negative 1800 joule. Okay, so the final answer is 11700 joule. Okay, so we talk about these energy conversions, and that will lead to the first law of thermodynamics. Okay, we have few laws of thermodynamics. Here is the first law of thermodynamics. That goes, it's a law of the conversion of energy. The total energy of the universe is constant. Or if, say, the energy change of the universe equals to the energy change of systems and surroundings, and it should be 0. Okay, basically, if you define everything together as a system, there's no surroundings, right? So then the energy change of the universe should be 0. In other words, energy cannot be created from nowhere. It has to be transferred from one to the other, one form to another form. Okay, so try to save energies used nowadays is actually from something else. And if we, consume too much or be too wasty, you're kind of converting all the energy from useful energies to less useful energies, and it's not a good thing. All right, this is the end of this video. I'll see you next time.